to confuse them. So I just want to differentiate between differentiability and continuity. But they're related, and so that's the thing about learning. You have to compare and contrast and know what's similar, what's different, okay? So what is differentiability? Finding where a function is or is not differentiable, right? So a function that fails to have a derivative at a point on the graph is non-differentiable. Okay, a function a function is non-differentiable if it fails to have, I'm sorry, it's so hard to see that. What happened? Fails to have a derivative. Fails to have a derivative at a point where the graph has a. Okay, so where are the places where where a function will be non-differentiable? They will be non-differentiable if there's a corner, a cusp, a vertical tangent, or a discontinuity. And actually there's a few more, but they're kind of encapsulated in these. Okay, I don't want you guys to, oh man, how does that work? Okay, so I'm gonna go to my little cheat sheet, which actually, if you have your book, you could just look at it too, it's in your book. On page 109. So corner, cusp. Okay, so a corner will look like this. A corner, obviously. Okay, like an absolute value or like the one that we saw yesterday. A cusp looks like this. Like a crack or, yeah. Okay, a cusp. And then a vertical tangent. Let's see, which example does it use? Okay, we can talk about like this. Okay, and a discontinuity can be such as this. Okay? So corner, cusp, vertical tangent, and discontinuity. Okay? Okay, so why would there be a why is there no derivative? Okay, why does the function fail to have a derivative at this corner? Wait, where? Does that mean there's no derivative anywhere? No, right here at x equals 0, there's no derivative, right? There's a there's a non-differentiability at x equals 0. Why? Say it again? The left and the right? Okay, so we could say the one-sided derivatives differ. Yeah? Does that make sense to you, the way I said it? The one-sided derivatives differ? Yeah, because the derivative, the left-handed derivative, does not equal the right-handed derivative, right? Because the derivative is a slope. Here the slope is negative, and here the slope is positive, and in the middle, you can't be negative and positive at the same time, right? What about a cusp? Why does the cusp By the way, an example, this is the function, so this is y equals absolute value of x. This is y equals, one example is x to the 2/3, okay? What happens here? So think about the slopes are, what's happening to the slope here? It's getting, is it positive or negative? Negative. And is it increasing or decreasing? Increasing. It's getting steeper and steeper and steeper until at the cusp, what do you think it's approaching? No, that slope is approaching. It's getting steeper and steeper, you said, right? Really, really, really big number, right? It's steep and steep and steep. It's steep and steep and steep and so steep over here. It's almost on a vertical line, huh? So the slope is very steep. So the slope is approaching what? The secant lines are approaching what? The slope is approaching infinity, right? Yeah? What about over here? The slope is positive or negative? Positive, and as we get closer to 0, it's getting steeper and steeper and steeper, so it's approaching infinity. So what are we approaching here? Negative infinity. What are we approaching here? Positive infinity. So do the left-handed and right-handed limits match? No. So it's still a corner.
Wait, why is it reaching negative?
Because it's really, really steep. So this is a negative slope though. So it's like negative 1,000 here, and it's like a positive 1,000 here. Okay, so we can say the left, so it's an extreme case of the corner. Okay, so left-hand derivative approaches negative infinity, and the right-hand derivative approaches positive infinity, so they don't match. Okay, it's an extreme case of a corner. This is a graph of x to the 1/3. Okay, what's the problem here? Okay, we're all looking at x equals 0, okay? We're just saying there's a non-differentiability at x equals 0. They're both positive, you're right. Okay, so let's look at the slope here. I need like a... Okay, so let's look at the slope. It's like positive or negative? Positive, and it's getting steeper, right? It's approaching what? Positive infinity. And over here, the slope is still positive. The whole time it's positive, but at this point, it's really steep. From the right, it's also approaching positive infinity. So we're approaching positive infinity from the left and the right. So it's not a problem with the derivatives not matching, but what is the derivative approaching? Infinity, positive infinity. Can we have a derivative of infinity? Can you have a slope of infinity? Is infinity a number? Infinity is not a number.
So can we say that for
I guess, but they were, I mean, the bigger problem, yeah, you could. But the bigger problem is they don't even match. Even if the infinity was a number, it wouldn't match, you know? Plus, a vertical line, what is the slope of a vertical line? What's the slope of 0? Horizontal slope 0. So what's a vertical slope? Undefined. So if the slope is undefined, then obviously the derivative, which is the slope, is undefined. So the slope is undefined. So there is no derivative there. So therefore, it is not differentiable there. Does that make sense? So yeah, you could say that. So let's say. Okay, so because it's a vertical tangent. So okay, that's what we call a vertical tangent. So the tangent is there. Yeah, there is a tangent, but the tangent is. So in a sense, there is a tangent slope. It's not that there's no tangent. It's just the tangent is vertical, right? The slope of the tangent is vertical, right? Therefore, is undefined, right? The slope is undefined. Okay, the slope is undefined. We can also say that the slopes of the secants, right, approach positive or negative infinity. And we don't like that. Okay, so what about this one? This is called a what? What kind of discontinuity? What are the? Let's talk about what are the different types of discontinuities we have. Jump, removable, oscillating, and infinite. The ones that we see the most are these two, right? Removable is another word for that. It's a hole, right? There's a hole. It's removable, but it's still discontinuous, so that's a hole. Right? We could call that a hole. Okay. So I gave you an example of a what? A jump discontinuity, but we could have very well put the other ones there. Okay? The jumps and holes, or jumps or removable discontinuities. What's the problem with those? If it's not continuous, why would it not be differentiable? The limit doesn't exist. Well, yeah, the left-hand limit does not match the right-hand limit, or the limit doesn't exist.
The limit.
So if the limit doesn't exist, then can we have a derivative there?
No.
What about if there's a hole? If there's a hole, the limit exists. The limit exists.
Okay. Yeah, that's not.
It's just not continuous, right?
Because that doesn't change the slope of the line.
Right. So does a derivative exist?
Yeah.
Is there a derivative at this point?
Maybe not at that point.
Is there a derivative at this point?
No.
You can't have a derivative if there's no point there,
Because then there's no slope there.
right? So what if the graph is like this? So what's the derivative at, if this is, at x equals 2, what's the derivative? I don't know, right? So obviously if there's a hole or a jump, then we cannot have a derivative, right? Does that make sense? Robert, does that make sense?
No.
Well, obviously.
Yeah.
You missed it. Okay, so what can we say? Either, so we can say either the one-sided derivative or both. Wait. Are non-existent. Ooh, sorry, that's messy. Okay, so we're going to learn a song that just helps us to remember this. I should have printed it out for you. But maybe you guys, do we have musical people in here? Maybe you guys can help me figure out how to add to this song, because by the end of the year, students always forget what this song is about because the song doesn't have the word differentiability in it or non-differentiability in it, so then they always confuse it with a constant, like they think it's a continuity song. So it goes like this. It's just head, shoulders, knees, and toes, and we'll get up and do some hand motions in a second. Okay. Oh, I have a guitar too, but we don't do that. Because corners, cusps, jumps and holes, jumps and holes. Corner, cusps, jumps and holes, jumps and holes. Vertical tangents and asymptotes. Corners, cusps, jumps and holes, jumps and holes. Get it?
Yeah.
Okay. Ready? 1, 2, 3. Corners, cusps, jumps and holes, jumps and holes. Corners, cusps, jumps and holes, jumps and holes. Vertical tangents and asymptotes. Corners, cusps, jumps and holes, jumps and holes. Okay. All right, hold on. So let's just check. Corners, that's here. Cusps, jumps and holes are both discontinuities. And then vertical tangents are here, and I didn't mention it here, but vertical asymptotes as well. Vertical asymptotes as well are not continuous.
Attention teachers, sorry for the interruption. Apparently some cars are blocking the trash cans in the back parking lot. If you could please move them so that we may get the garbage removed. Once again, there's cars that are blocking the dumpsters in the back, so we can't take the trash out. Can you please move your car? Thank you.
I don't think, yeah, I don't think I'm blocking a bin, but I don't think it's a trash can. Carlos Samosa.
Done. FaceTime real quick. Did you record us singing the song?
Oh yeah, this is still deleting. I mean deleting. I just deleted a message, that's why. Okay, why don't you guys practice while I'm texting? Okay, ready? 1, 2, 3. Keep going. 1, 2, 3, 4.
Where were you at?
All right, so jumps and totes. Now, if you think about a vertical tangent and an asymptote, a vertical asymptote, if I had a graph and there was a vertical asymptote, let's say like here, and the graph looked like this, maybe like a hyperbola, obviously that is a vertical asymptote, but also that's not that's a discontinuity already. So, oh, that's an infinite. Oh, that's what this is.
Then you can still find the slope of the line.
At x equals 2 at this point though. So that's right here. That's called a infinite discontinuity anyway. Right? So technically we already just included it right here. Right? So write that in, vertical, because a vertical asymptote is an infinite discontinuity, right? All right, so now we're going to add the hand motions and some spirit, okay? So everybody needs to get up after you write vertical asymptotes. Okay, everybody get up.
Get up, great. Stand up.
Yeah.
Feet.
Yeah, on your feet. Así es. Okay?
I think I can. Alright, other turn.
Okay. So, and I could get out my swivel camera and like videotape us.
Whoa.
Okay. All right. So it goes like this. Well, what do you think? Corners. Wait, we're waiting for everybody to get up. Corners, cusps, jumps.
Oh, I can't. Shaking here.
Jumps and holes. Corners, cusps, jumps and holes. Jumps and holes. Okay. Okay. Vertical tangents and asymptotes. Get it? Corners, cusps, jumps and holes. Jumps and holes. Okay.
So like in the middle of the AP test, so we're just gonna.
Yeah. But see, we need to add something to the song so we know. Remember that this is non-differentiability.
Non-differentiability song.
Okay, we could go 5, 6, 7, 8. Non-differentiable. Corners, cusps, jumps and holes. Jumps and holes. Corners, cusps, jumps and holes. Jumps and holes. Vertical tangents and asymptotes. Corners, cusps, jumps and holes. What? What is it?
Oh, look at it.
That's a big button.
Really?
No, let's just let it out.
That's so
You should use it from the other side.
Stop.
You need two papers. Oh. You know what? Let's just cage it up for now.
We're distracted a bit. The lesson has disappeared.
It's hard. There.
Watch you start moving.
I was like, why aren't you singing? Alright. Okay, ready? Okay. So I'll say 5, 6, 7, 8. You have to say
What if you have
non-differentiable.
family?
Okay? Ready? 5, 6,
She's
7,
staring
8.
at it.
Non-differentiable. Corners, cuts, jumps and holes, jumps and holes. Corners, cuts, jumps and holes, jumps and holes. Vertical tangents and asymptotes. Corners, cuts, jumps and holes, oh, jumps and holes. Okay, now we have to sing it faster. And if you're not doing it, you're going to be made to do it by yourself.
Oh, hey.
Okay, so make sure you're doing it.
Granny Speedy
Okay.
style right now.
Okay, so let's go faster. 5, 6, 7, 8. No. That's what I don't remember, okay? 5, 6, 7, 8. Non-differentiable. Corners, cuts, jumps and holes, jumps and holes. Corners, cuts, jumps and holes, jumps and holes. Vertical tangents and asymptotes. Corners, cuts, jumps and holes, jumps and holes. Can you do it faster?
No.
Yeah, you gotta do it really fast, like this. 5, 6, 7, 8. No, okay, that's not hard. 5, 6, 7, 8. Differentiable. Corners, jumps and holes, jumps and holes. Corners, cuts, jumps and holes, jumps and holes. Vertical tangents and asymptotes. Corners, cuts, jumps and holes, jumps and I don't see the spirit there. I think this guy wants to do it by himself.
Guys.
Alright, you guys, sit down, sit down. Alright, so that's one of many songs that we'll learn this year.
Got a little hot in this room for us.
Okay, that's how I feel all day though, teaching. That's how I feel, because I feel like I'm running around. Okay, so differentiable functions. Yes, yes, because it's really hot when you're teaching. Okay, so most of the functions, alright, so most of the functions that we encounter are differentiable. Okay, so that means we will not, most of the time, you're not going to have a corner, or a cusp, or vertical tangent, or point of discontinuity. The grass will be smooth and unbroken and smooth with a well-defined slope at each point. Polynomials are differentiable, as are rational functions. I'm going to write this down. Polynomials, rational functions, all the ones that were are continuous for us, they're also differentiable. I'm writing this down on the line right there. Trig functions, I'll show you in a second. Exponential functions and log functions. Okay, compositions of the above. Okay. Okay? Why is it doing that? Okay? Polynomial functions, rational functions, trig functions, exponential functions, log functions, compositions of the above are all differentiable everywhere. Okay? Okay, what is a differentiable function? It's a function that's differentiable everywhere as long as we're in its domain. Not everywhere in the world, just everywhere in its domain. Okay? And so, the thing is, people, we're not going to be able to finish. Oh, man. Oh, man. Okay, there's nothing else we can do about it. I'm going to have to finish the lecture on a video because I cannot have you go this whole weekend not going further. So, so I was going to say, are you going to come tomorrow?
No,
Are you gonna come over? Are you gonna do the example?
So I was going to just have you guys learn it from the book because it's all in the book. But we're not that good at that yet. So, okay, so you already did this, right? Today is, yeah, to 18th. So yesterday you did this. So over the weekend you're going to do this. Okay, so when I say, okay, I'm going to show you a video to finish these notes. Okay, what day is it today? Thursday? I'll do my best to post it by tonight. Okay? If not tonight, then by tomorrow. Okay? And I want you to read the book. Okay? Especially for this chapter. 3.2, just glance over everything. Just kind of read through to make sure you're not missing any of the connections, okay?
Do on Monday?
Yes. Due on Monday. See, man, I didn't get to check your homework either. That's why I used to do those quizzes. That gives me time at the beginning of class to check your quizzes.